I want to talk about drawing Lewis structures for compounds. And what we use Lewis structures for is to show the number of bonds between atoms and the number of non-bonded electrons in a molecule. So, for instance, if we look at a molecule such as SO2, the Lewis structure would look like this. This structure shown here, where these dots represent pairs of electrons, and we have the S for sulfur, the O for the oxygens. And what I want you to notice is that on this side right here, the right side oxygen, this sulfur and this oxygen share one pair of electrons, and so that represents a single bond. Whereas on the other side over here, they share two pairs of electrons, and that represents a double bond. And this two shared pairs of electrons is what we refer to as a double bond. Now, I also want you to notice that there are some pairs of electrons that are not shared, and these are called either non-bonded electrons or lone pairs of electrons. A couple of other features I want you to notice about these Lewis structures are that if you count up all of the electrons that an atom in this particular molecule, SO2, either has by itself, the non-bonded or lone pairs, or that it shares in a double or single bond, it adds up to 8. So if we summarize that, we can say that the number of electrons an atom has around it that it does not share, the lone pairs, or does share in single, double, or not applicable for this molecule, but triple bonds usually adds up to 8. There are some exceptions to that. We're not going to worry about those exceptions right now. So for instance, in this molecule, if we look, for instance, at the oxygen on the left, this oxygen has 4 non-bonded electrons, 1, 2, 3, 4, and 4 shared electrons in the 2 bonds it forms, 1, 2, 3, 4, and that adds up to 8. If we look at the sulfur, it has 2 non-bonded electrons, 1, 2, and then a total of 3 bonds, 2 bonds on the left, 1 bond on the right. Each bond contains 2 electrons, that's 6 shared electrons for a total of 8. And I could do the same thing for the oxygen on the right. It would have 2 shared electrons and 6 unshared electrons, again, for a total of 8. Now, another thing I want to point out to you is something that we've been doing is we've been saying that a pair of shared electrons represents a bond. And that is definitely something you want to become familiar with because it's something we're going to see over and over again. A pair of shared electrons is what we refer to as a covalent bond. And that, as I said, is something you definitely want to remember and get used to. And because of that, sometimes instead of drawing our Lewis structure like this, we will do the following. We'll represent our Lewis structure like this, where the covalent bonds, the shared electrons between atoms, are represented as a line. But it's important for you to remember what those lines mean. This single line represents one pair of shared electrons, whereas this set of 2 lines represents 2 pairs of shared electrons. Now, what I want to talk about is how we actually go about and draw this structure. When I see the formula SO2, how do I know that I'm supposed to draw something with 2 bonds between sulfur and oxygen on one side, 1 on the other, and 1 pair of unshared electrons here, 2 here, and 3 here, and so on? Well, there are a series of steps or rules that I suggest you go through, and I want to look at those now. The first molecule I want to look at, and I want to use as an example, is this one right here where we have H2CO. And for a molecule like this, you're going to have to be shown the sort of order that atoms are connected in. So for this molecule, the connectivity looks like this, where this carbon and this hydrogen is bonded together. It's bonded to this hydrogen and this oxygen also. So I'm actually just going to go and show that connectivity like this. And we need to remember that this line represents a pair of shared electrons. Now, I'm going to strongly suggest that when you do this, you don't randomly try to figure out the right Lewis structure, but you follow a series of rules. And I'm going to lay out my suggestion as to the steps that you take to do this. And the first thing that we want to do is to count the number of valence electrons in the molecule. So we're going to look at how many valence electrons each of these atoms have and add them up. We've got one oxygen with 6 valence electrons, so 1 times 6 equals 6. We've got one carbon, and it has 4 valence electrons, so 1 times 4 is 4. And finally, we've got 2 hydrogens, each with 1 valence electron, so 2 times 1 is equal to 2. Now, that means that our molecule that we're trying to draw the Lewis structure for has a total of 12 valence electrons. Now, it's important to remember, and I should have mentioned this earlier, that the Lewis structure, we're only showing the valence electrons. And whatever structure we draw for this molecule is going to have 12 electrons represented. So what we do next, now that we know how many electrons we should have in the end, is we go and we give every atom an octet. So all atoms are going to end up with an octet, by which we mean 8 electrons, except for hydrogen. Hydrogen only has 2 electrons. So let's go and do that for this molecule. And our structure will look like this, where the oxygen has 2, 4, 6, and the shared pair for 8. This carbon has 2 shared here, 2 shared here, 2 shared here, and 2 unshared for a total of 8. And each of these hydrogens only has the single line connecting it because hydrogen only gets 2. This line represents 2, so each hydrogen has 2 shared pairs. Well, now we've drawn everything having an octet. Let's go and count how many electrons we've actually shown. So if I count them, I've got 2, 4, 6, 8, 10, 12, 14 electrons. Well, that's no good that I have shown 14 electrons because I know that I'm only supposed to have 12. So I need to do something to get the total number of electrons in my structure down to 12. But I still want to make sure all atoms have an octet. So those are the 2 conditions I need to meet now. Still keep everything with an octet, but get 2 fewer electrons. And what we're going to do is the following. If after giving all atoms an octet, which we did, you have too many electrons, which we do, remove 2 pairs, and that should be a little bit more specific. It should say 2 pairs of unshared electrons, or 2 lone pairs, and add 1 double bond. So that's what we're going to do here. I'm going to remove a lone pair from here. So let me just take it and move it over there. So I've removed 2 electrons, so now I have a total of 12 electrons. And you might say, oh good, we have 12 electrons, so we have the right number of valence electrons, but now this carbon only has 2, 4, 6 electrons around it. And we want to make sure all atoms keep an octet. So what I'm going to do is I'm going to remove 2 more electrons from here. And you might say, oh no, now we're in trouble. We only have 10 valence electrons and we want 12. Well, I fix that by adding another pair that's shared between those 2 atoms, the carbon and the oxygen. Now both of these have 8 electrons. The carbon has 2, 4, 6, 8 shared electrons. The oxygen has 4 shared and 4 unshared. And I have a total of 2, 4, 6, 8, 12, 14, I'm sorry, I counted wrong. 2, 4, 6, 8, 10, 12 valence electrons, which is what we want. So we've got the correct Lewis structure. Now, there are going to be some times that even after we do this last step that I just did here, after giving all atoms an octet, you have too many electrons, remove 2 lone pairs and a double bond, we're still going to have too many electrons. For instance, in the molecule C2H2, which has a connectivity shown here, if we count up the number of valence electrons we should have, doing it the same way we did up top, we find that we should have 10 valence electrons in the final structure that we draw, 8 from the 2 carbons, 2 from the 2 hydrogens, and when we go and do the second step, which is to give all atoms an octet, remembering that hydrogen doesn't get an octet, each hydrogen only has 2 electrons, we get a structure like this, which has a total of 2, 4, 6, 8, 10, 12, 14 electrons. So I go through this process one time and remove a pair of electrons from here and from here, and add an extra bond. I still have, if I count up my electrons in this structure, 2, 4, 6, 8, 10, 12, which is still too many. So what I have to do is I have to do this a second time. I have to remove these electrons and remove these electrons, and then I need to make sure I still have an octet by adding another bond. And now I have the right number of electrons. I want to look at one more example, and that example is NO2 minus 1. And you'll notice that this molecule has a charge on it, and one of the things that we need to do when we have charges is the following. We account for that charge by adding 1 to the total number of valence electrons we should have for a minus charge. If this had a positive charge, we would subtract 1 from the total number of valence electrons it should have. So for this molecule NO2, the nitrogen gives us 5 valence electrons, the 2 oxygens gives us a total of 12 valence electrons for a total of 17, but we have a minus charge on here, so we have to go and add 1 to that total for a total of 18 valence electrons. Now, when we draw the connectivity of this, it's going to look like this. The nitrogen goes in the middle because it's the less electronegative atom, and the less electronegative atom almost always goes in the middle of our Lewis structures. So if I go and give all of these atoms an octet, I get this structure. If I count the electrons in this structure, I find I have 2, 4, 6, 8, 10, 12, 14, 16, 18. Let me double check. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. It's always a good idea to double check your count. It comes out to be 20. I've got 2 too many, so I need to remove 2 from here. So let me do that. 2 go here, 2 from here, and I need to replace 2 of those 4 with an extra bond, and that's my final Lewis structure. And what I usually do, because I have a -1 charge on this and I have to show that charge, is I will put a pair of brackets around this. And I'll also put the -1 charge up there to represent that there's a -1 charge on this molecule. Now you may have noticed that I could have drawn the multiple bond between the nitrogen and the other oxygen. That would have been correct too. That's something called a resonance structure, which we're not going to worry about in this presentation today.